My name is Ms.K.Nithyakalyani. I am going to share you about the chapter alkanes. Introduction. Alkanes. Organic chemistry, it is the study of hydrocarbons and their derivatives. The derivatives are prepared by replacing one or more hydrogen atoms with suitable groups from the corresponding hydrocarbons. Thus, the hydrocarbons are the parents of the hydrocarbons. So, alkanes is nothing but organic chemistry. It is the study of hydrocarbons and their derivatives. The derivatives are prepared by replacing one or more hydrogen atom with suitable atoms or the groups from the corresponding hydrocarbons. So, organic chemistry is nothing but it is the study of hydrocarbons and their derivatives. The derivatives are prepared by replacing one or more hydrogen atom with a suitable atom group from the corresponding hydrocarbons. Thus, the hydrocarbons are the parents of organic compounds. The studies on the structures, method of preparation, properties of hydrocarbons are the basic units of organic compounds, and that are very essential for further studies in this important branch of chemistry. Hydrocarbons are mainly of two types, saturated as well as unsaturated. In saturated hydrocarbons, the valency of the carbon tetracovalent is fully satisfied, whereas in unsaturated hydrocarbons, it is not fully satisfied. The saturated hydrocarbons are CCCH single bonds only, whereas unsaturated hydrocarbons have a carbon double bonds also and then carbon triple bond also. Carbon hydrogen bond is them. In this chapter, we will be taking up the study of saturated hydrocarbons in the alkanes. So, organic chemistry is nothing but it is the study of the corresponding hydrocarbons and their derivatives. So, the derivatives are prepared by replacing one or more hydrogen or carbon atom, the suitable atomy of the group. Thus, the hydrocarbons are the parents of organic compounds. The studies on the structures and the method of preparation and their properties of the hydrocarbons being the basic units of the organic compounds that are very essential for the further studies. And this is important for the branch of chemistry. Hydrocarbons are mainly of two types, saturated hydrocarbon as well as unsaturated hydrocarbon. In the saturated hydrocarbons, the valence of the carbon tetracovalent is fully satisfied, but in unsaturated hydrocarbons, carbon hydrogen bonds, carbon double bond is there. In this chapter, we will be making it as saturated hydrocarbons, especially alkanes. We are going to see structure of alkanes. In alkanes, all the carbon atoms linked through the single covalent bond. They are undergo sp3 tetrahedral hybridization. Let us illustrate the structure of alkanes by taking the examples of first two numbers, namely methane as well as ethane. So, methane is also an alkane, ethane is also an alkane. In alkane, all the carbon atoms linked through the single covalent bond. So, they undergo sp3 tetrahedral hybridization. Let us illustrate the structure of alkanes by taking the example of first two numbers, namely methane as well as ethane. In alkanes, all the carbon atoms are linked through the single covalent bond. They undergo sp3 tetrahedral hybridization. Let us illustrate the example. Let us take the example for methane as well as ethane for the structure of alkanes. Orbital structure of methane, it is a sp3 hybridization and then it undergoes a tetrahedral rearrangement. In the formation of the methane, each sp3 hybrid orbital of carbon overlap with the 1s orbitals of 4 hydrogen atoms to form 4 carbon hydrogen bond as shown in the figure. In the formation of methane, each sp3 hybrid orbital of the carbon overlap with the 1s orbital of the 4 hydrogen atoms to form the carbon hydrogen bond. That is CH4 is the carbon with the 4 hydrogen atoms or a bond. So sp3 hybridization is linked through the sigma bond here, and then bond angle between the carbon hydrogen is 109.28 and then carbon hydrogen is 1.10 angstrom. Orbital structure of a methane, 2D representation as well as a 3D representation is also there. We have to draw this diagram. So thus the methane molecule has a symmetrical tetrahedral structure. Each carbon hydrogen bond length is 1.10 angstrom and carbon hydrogen bond angle is 109 degree 28 angstrom. So thus the methane molecule has the symmetrical tetrahedral structure. Each carbon hydrogen bond length is 1.10 angstrom or 110 ppm and carbon hydrogen bond angle is 109 degree 28 angstrom. That is methane molecule has a symmetrical tetrahedral sp3 hybridization. Carbon hydrogen bond length is 1.10 angstrom and then carbon hydrogen bond angle is 109.8. For the sake of convenience, methane is also represented in the figure. In this figure, the thick heavy lines indicate the carbon hydrogen bond projects towards the reader, and the normal line carbon hydrogen bond is the plane of the page, and the two dotted lines carbon hydrogen bond projected within the plane of So what they are trying to say is, for the sake of the convenience, methane is also prepared in the figure. In the figure, the thick heavy lines indicate carbon hydrogen bond projection towards the reader. The normal line carbon hydrogen bond in the plane of page, and the two dotted lines carbon hydrogen bond projecting behind the plane of the page. In this, it is called as a spatial formula. For the sake of convenience, methane is represented in the figure. A thick, heavy lines carbon hydrogen bond projecting towards the reader. Normal line carbon hydrogen bond in the plane of the page, and the two dotted lines carbon hydrogen bonds projecting behind the plane of the page. It is called as a spatial formula for 3D representation. The two-dimensional representation of the methane molecule is shown in the figure. It is called as a graphic 2D representation. For common purpose, such a representation is always used. In similar manner, ethane, propane are depicted as a CH3 is ethane, and then propane 3 carbon atoms. So C2H5. Okay. So orbital structure of ethane, structure of carbon single bond. The formation of ethane. Orbital structure of ethane, structure of a carbon single bond, and formation of the ethane. First point, one sp3 hybrid orbital of each two carbon is axially to form a carbon-carbon sigma bond. The remaining 3 sp3 hybridized orbitals of each carbon atom overlap with the 1s orbital of hydrogen atom to form CH bond as shown in the figure. So one sp3 hybrid orbitals of each of the two carbon atoms are axially to form a carbon-carbon sigma bond. The remaining 3 sp3 hybridized orbital of each carbon atom overlap with the 1s orbital of a hydrogen atom to form 6 carbon hydrogen bond as shown in the figure. So in this one sp3 hybridized orbitals of two carbon atoms are axially to form carbon-carbon sigma bond. Yes, and then here the remaining 3 sp3 hybridized orbitals of each of the carbon atom overlap with the 1s orbital of the hydrogen atom to form a carbon hydrogen bond as shown in the figure. So see here 1, 2, 3, 1, 2, 3. So bond length between a carbon is 1.54 Armstrong, and then a carbon hydrogen is 109.28. Here carbon hydrogen bond length is 1.10 Armstrong. So structural isomerism. Alkane shows the chain isomerism, which may be defined as the phenomenon in which a same molecular formula represents two or more compounds having a different structural formula due to the different arrangement of the carbon chain. Such compounds are called as a chain isomers of the skeletal or nuclear isomers. So alkane shows the chain isomerism, which may be defined as the phenomenon in which a same molecular formula represents two or more compounds having a different structural formula due to the different arrangement of the carbon chain. So alkanes is nothing but chain isomerism, which can be given as a phenomenon in which a same molecular formula but different structural formula due to the different arrangement of the carbon chain. Such compounds are called as the chain isomers or the skeletal or nuclear isomers. So in alkanes, the first three members, methane, ethane, propane, or do not show any chain isomerism because only one arrangement of the carbon atom is possible. So butane and higher alkanes will always show the chain isomerism. Chain isomerism is C4H10. It has two chain isomers, N-butane, CH3, and then isobutane. A secondary carbon atom will have a hydrogen as well as a methyl group is said to be iso. So methyl propane as well as isobutane. So chain isomerism, it has two chain isomers. Chain isomerism in pentane, isopropane and neopentane, isopropane as well as pentane. Here N-pentane. Chain isomerism in hexane, N-hexane, isohexane, 3-methylpentane, 2,3 dimethyl-butane, neohexane. General method for the preparation of alkanes. So before that, we can recall once again. So what do you mean by alkanes? Organic chemistry, it is the study of hydrocarbons in their derivatives. The derivatives are prepared by replacing one or more hydrogen atoms with the suitable atoms or the groups which corresponds to hydrocarbons. Thus, the hydrocarbons are the parents of the organic compounds. The studies on the structure of the method of preparation properties of hydrocarbons being the basic units of the chemistry. So in this hydrocarbons, there are mainly of two types, saturated as well as unsaturated. Here we are going to see about the saturated. Structure of alkanes shows the sp3 hybridization tetrahedral rearrangement. In alkanes, all the carbon atoms linked through the single covalent bond. They undergo sp3 tetrahedral hybridization. Let us illustrate the structure of alkanes. Methane as well as ethane. Orbital structure of methane. In the formation of methane, each sp3 hybrid orbitals of a carbon overlap with the 1s orbitals of the 4 hydrogen atoms to form a 4 carbon hydrogen bonds as shown in the figure. So here, orbital structure of methane. So this is the orbital structure of a methane. 3D representation also given and 2D representation is also given. Thus, the methane molecule has a symmetrical tetrahedral. Carbon hydrogen bond length is 1.10 angstrom and hydrogen carbon hydrogen bond length is 109.28 dash. For the sake of convenience, methane is also represented in the figure. Thick heavy lines indicate carbon hydrogen projecting towards the reader. The normal line carbon hydrogen in the plane of the page, and the two dotted lines carbon hydrogen projecting behind the plane of the page, into the, behind the, and then towards the. It is called as a spatial formula or 3D representation. The two-dimensional representation of the methane molecule is shown in the figure. It is called as a graphic or 2D representation. For a common purpose, such a representation is always used. In similar manner, ethane, propane are depicted as follows. So ethane here, CH3, CH3, and then propane is also given 3 carbon atoms. CH3, CH2, CH3. Orbital structure of ethane. Structure of the carbon atom, single bond in formation of ethane. Orbital structure of ethane. Structure of the carbon-carbon single bond and the formation of the ethane. One sp3 hybrid orbital of each of the 2 carbon atoms are axially to form a carbon-carbon sigma bond. The remaining 3 sp3 hybrid orbitals of each of the carbon atom overlap with the 1s orbitals of the hydrogen atom to form a 6 carbon hydrogen bond as shown in the figure. So one of the sp3 hybrid orbitals of each of the 2 carbon atoms are axially to form carbon-carbon sigma bond. The remaining 3 sp3 hybrid orbitals of each of the carbon atom overlap with the 1s orbitals of the 2 hydrogen atoms to form carbon hydrogen bond as shown in the figure. Okay, structural isomerism. Alkane shows a chain isomerism, which may be defined as a phenomenon in which the same molecular formula but different structural formula due to the difference in the carbon chain. Different in the molecular arrangements of the carbon chain. Such compounds are called as a chain isomers or the skeletal or the nuclear isomers. In alkanes, the first 3 members of methane, ethane, and propane, it does not show the chain isomerism because only one arrangement of the carbon atom is possible. Butane higher alkanes shows a chain isomerism. Here, only one carbon atom arrangement is possible, but in butane it is 2 is possible, and then chain isomerism here 3 is possible. Pentane and then hexane it has 5 is possible. Generation of the alkanes. So, from the unsaturated hydrocarbons containing a double and triple bonds can react with the hydrogen in the presence of finely divided nickel, palladium, and then platinum to form a alkane. CnH2n plus H2 is equal to, in the presence of a nickel, it forms CnH2n plus 2. For example, ethene. CH2 double bond CH2 plus H2. ENE is converted into ANE in the presence of nickel. So hydrogen atom is added here. One hydrogen atom is added here. Double bond is breakdown, and one hydrogen atom is added here. CH3, CH3. So propene, CH3, CH, double bond CH2. Here one hydrogen atom is added, and here one hydrogen atom is added. So CH2, CH3, CH3. From alkynes. So CnH2n minus 2 plus S2 is equal to CnH2n plus 2. Yes, I have one hydrogen atoms are added, so plus 2. So CH double bond, triple bond CH plus 2 H2. So CH3 ethane. Triple bond is broke down. So here triple bond is broke down. And then CH2, CH3, CH3 hydrogen. Here 2 hydrogen atoms. Here 2 hydrogen atoms. So CH3, C triple bond CH plus 2 H2 means here also propane is formed. Platinum as well as palladium and nickel are more active catalyst and can be bringing about the hydrogenation even at a room temperature. But with the nickel higher temperature, 523 to 573 degrees C is required, and the reaction is known as the Centrinus reaction. Nickel is active form of nickel, and it is sometimes penetrating Ni and Al alloy with the sodium hydroxide, and Al dissolves, leaving Ni in the finely divided state. So platinum as well as palladium as well as nickel are the most active catalysts and can be bringing up the hydrogenation even at the room temperature. But with the nickel higher temperature, numerator, it is required. The reaction is known as a centrinous reaction. Ranai nickel is an active form of a nickel, and it is obtained by treating a nickel and alloy with the sodium hydroxide. When aluminum dissolves, leaving Ni in the finely divided state, the yield of the alkane is very high. Methane, however, cannot be prepared by this method, and it is starring alkanes and must contain at least 2 carbon atoms. So we have seen about from alkene and alkyne, how the alkane is getting ready, and then from here alkyl halides. Alkyl halides general formula is for alkyl group or an halogen group X2 or X. So halogen like a Cl bromine and iodine we are using here, and then alkyl halides are converted into alkanes by reduction or by Wood's reaction or by Corey-House reaction or Franklin reaction. Reduction of the alkyl halides. Different reducing agent can be used for reducing the alkyl halides to obtain alkanes. So nascent hydrogen produced by zinc as well as HCl or zinc or NaOH. Zinc acetic acid and zinc copper or alcohol reduction halides to alkane. So RX plus 2 nascent hydrogen, it gives alkane plus HX. So here C2H5I plus 2 hydrogen atoms, it gives C2H6 ethane plus hydrogen iodide. So CH3, CH2Br, CH3, that is 4 carbon atoms. So second question, the bromobutane, it gives butane as well as a hydrogen bromide is eliminated. So catalytic reduction, alkyl halides can also be reduced by hydrogen in the presence of palladium as a catalyst. So it is done by Woods as well as Corey-House as well as a Franklin reaction. So here we are using a zinc metal and then copper ethyl alcohol. Catalytic reduction we are using here is a palladium as a catalyst. Alkyl halides can also be reduced by hydrogen in the presence of palladium as a catalyst. C2H5Br plus H2, C2H6 plus hydrogen Br. Hydroiodic acid HA is a powerful reducing agent, and that reduces alkyl halides, particularly iodides, to alkanes under pressure plus at 420 K. C2H5, that is ethyl iodide, it reacts with hydrogen iodide to red hot to form C2H6 ethane plus iodine. Iodine produced may be react with alkane to avoid the phosphorus is added. Red phosphorus is added. So next here, 2p plus 3 iodine, it gives 2pi3. So alkyl halides can also be reduced by complex metal hydrates like lithium aluminum hydride and then NaBH4 plus LiAlH4 reduces the primary secondary alkyl halides, while NaBH4 reduces only the secondary tertiary alkyl halides. So 4 or X, it reacts with the lithium aluminum hydride to form 4 or H plus LiAlH4. The reduction takes place in the 4 independent steps, each step involving the nucleophilic displacement by hydride ion H minus. When alkyl halide is treated with a metallic sodium in the presence of dry ether, a symmetrical higher alkane is formed ascending of a series. The method is used for stepping up of a homologous series, conversion of a lower member to higher member. So RX, alkyl halide plus 2 molecules of a sodium, it reacts with XR, dry ether, RR plus 2 NaX. So CH3I, methyl iodide, it reacts with 2 molecules of a sodium, iodomethane, iodomethyl in presence of a dry ether to form ethane plus 2 molecules of the sodium iodide will be eliminated, and then ethyl iodide reacts with the 2 molecules of the sodium, and then C2H5, dry ether, C2H5, iodine, 2 molecules of the sodium iodide will be eliminated. And then isopropyl bromide, it reacts with 2 molecules of the sodium in presence of a dry ether to form dimethyl butane. So dimethyl butane, and then 2 molecules of sodium bromide will be eliminated. So limitations: unsymmetrical alkanes. Alkanes containing an odd number of the carbon atoms cannot be prepared by this method. For example, suppose it is required to prepare a bromide for a mixture containing equimolar concentration of the methyl bromide and the ethyl bromide, ethane and butane are obtained as a byproducts. So, in case of a preparation of the propane, ethyl bromide and methyl bromide are obtained as byproducts. Here C2H5BR plus B or CH3 means C2H5 propane, CH3 is CH3, CH2, CH3 propane plus 2NaBr. So CH3Br plus 2Na plus Br CH3 means CH3 ethane plus 2NaBr. And then C2H5Br plus 2 molecules of the sodium plus Br C2H5 means C2H5 plus NaBr. Methane cannot be prepared by this method. This reaction fails with the tertiary alkyl halides. Wood's reaction is very useful for ascertaining the series of the organic compounds and involved in the formation of the new carbon-carbon bond. Two possible mechanisms depending upon the conditions of the reaction. It has been proposed. Ionic mechanism, it operates when the reaction is carried out with the solution. It's carried out with the solution. It has been suggested that an atom of the sodium reacts with an alkyl halide to form alkyl sodium compound having a quark anion character. The alkyl sodium thus formed provides a nucleophilic alkyl quark anion, which displaces the halide ion to form another molecule of the alkyl halide by SN2 mechanism, resulting in the formation of an alkane. So it operates with the reaction which is carried out in the solution. It has been suggested that an atom of the sodium reacts with an alkyl halide to form an alkyl sodium compound having a quark anion character. The alkyl sodium thus formed provides a nucleophilic alkyl quark anion which displaces the halide ion from another molecule of the alkyl halide by SN2 mechanism, resulting in the formation of an alkane. OH plus 2Na or Na plus NaX or X SN2 or X minus. Okay, halogen will be separated. This mechanism also explains the formation of the byproducts. For example, ethyl iodide on treatment with the sodium metal in the presence of ether, it gives the N-butane as a major product and ethene and ethane as a minor products. So this mechanism also explains the formation of the byproducts. For example, ethyl iodide and treatment with the sodium metal in the presence of ether, it gives the N-butane as the major products and ethene and ethane as the minor products. CH3 CH2 plus HCH2 CH2I means CH3 CH3 plus CH2 double bond CH2 plus I as so here shifting of a hydrogen atom here, so CH3 CH2 double bond CH2 plus I minus this bond will be break down and double bond will be formed. Free radical mechanism, when the reaction is carried out in a vapor phase, it can be takes place via free radical mechanism. Sodium metal first reacts with the alkyl halide to form alkyl free radicals, which may couple or disproportionate from the observed products RX plus Na or free radical plus NaX. So two molecules of the free radicals means or for example CH3 CH2 coupling reaction C2H5 free radical C2H5 free radical means C2H5 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 and the disproportionation reaction is a disproportionation reaction. So CH3 CH2 plus HCH2 CH2 free radical. So CH3 CH3 plus that is this hydrogen atom will be added here CH3 CH3 and this bond will be shifted here ethane as well as the ethene. House reaction. The reaction is better than Wood's reaction since it permits the formation of alkenes containing both the ever odd number of the carbon atoms. So higher alkenes included branched chain alkenes also may be prepared by this method. This method will develop in 1970. It consists of reaction between an alkyl halide and the lithium dialkyl copper. So this reaction is better than the Wood's reaction since it permits the formation of the alkanes containing both the even and the odd number of the carbon atoms. Higher alkanes included the branching chain alkanes also can be prepared by this method. This method was developed in 1970 and this consists of RX plus 2Li. So LiX 2R plus Li CuI means 2 or 2 CuLi lithium dialkyl copper and then triether means alkane. So this process the difference for good yields alkyl halide RX is generally the primary halide, but alkyl group is the organometallic compound. It can be prepared by primary, secondary and then tertiary. Either primary, secondary or tertiary. Okay, either primary, secondary or tertiary. CH3 CH2B or Li, CH3 CH2Li, CuLi means lithium diethyl copper, lithium diethyl copper. So next is CH3 CH2 twice CuLi plus N propyl bromide oda setom appadina dry ether pentane alkane is formed and then CH3 CH2 Cu and then LiBr, lithium bromide will be eliminated. So here Frankland's method, when alkyl halides are heated with a zinc in the inert solvent, higher alkanes are formed. So RX plus Zn plus XR or R dash plus Zn-X2, C2H5I plus Zn-I-C2H5 means C4H10 plus zinc iodide. So dialkyl zinc compounds react with the alkyl halides to give the hydrocarbons to the quaternary carbon atom only. So zinc react with the 2-methyl group dimethyl. Then 2-chloro, second question chloro, trimethyl propane. So 3-methyl group is attached to tertiary butyl chloride, and then neopentane is formed, and then a dimethyl propane. 2,2 dimethyl propane by using a Grignard reagent. Grignard reagent is the RMG. X is the alkyl group and X is the halogen atom. Whether it may be a chlorine, bromine, or iodine, it is obtained from the alkyl halide and the magnesium and the dry ether. For example, CH3 CH2Br plus Mg means CH3 CH2 MgBr. So it is the Grignard reagent. This compound reacts with the active hydrogen obtained from the water, alcohol, ammonia, and primary amine to form the alkanes. For example, CH3 CH2 MgBr plus water molecule, it gives ethane, MgOH(Br), and then ethyl magnesium iodide, it reacts with the methanol to form ethane plus MgIOCH3. For carboxylic acids, the general formula for the carboxylic acid is or COOH is a carboxylic or is an alkyl group. This the two methods of the alkanes is obtained in the carboxylic acids. By heating with the sodium salt of the acid with the soda lime, decarboxylation when the sodium salt of the carboxylic acid is heated with the soda lime. Carbon dioxide is lost as an alkane is formed. Process of elimination of the carbon dioxide is from carboxylic acid is known as the process of elimination of the carbon dioxide from the carboxylic acid is known as the decarboxylation. And then sodium hydroxide is taken out in the reaction whether the calcium oxide diffusion. So RCOO Na plus NaO, which means RH plus Na2CO3, sodium bicarbonate will be eliminated. Sodium carbonate will be eliminated, and then CH3 Na, sodium acetate, it reacts with sodium hydroxide to form a methane as well as sodium carbonate will be eliminated. Decarboxylation is the method of preparation of the alkane with one carbon atom less than the starting carboxylic acid. Designing of a series from the lower homologous, the yield of alkanes is good, but the higher homologous it is poor. A probable mechanism of this reaction is proposed as follows. So here HO free radical or C double bond OO or stands for alkyl group. So carboxylate ion. So here OH will be attached here, and then here what we are telling. See here that is R separated and then COH and then OH. Okay, then proton transfer. Proton transfer is nothing but hydrogen is shifted here, alkane, hydrogen is shifted here. So alkane will be formed. Carbonate ion will be eliminated. By cold electrolytic method, when a concentrated aqueous solution of the sodium and the potassium salt of the carboxylic acid is electrolyzed, a higher alkane is obtained as shown below. 2-or-COO-Na plus 2H2O, it gives electrolysis, or 2 plus 2NaOH plus hydrogen plus 2 molecules of the carbon dioxide will be eliminated. So when concentrated aqueous solution of the sodium and the potassium salt of the carboxylic acid is electrolyzed, a higher alkane is obtained as shown below. 2-or-COO-Na plus 2H2O, CO, it gives R plus 2NaOH plus H2 plus 2CO2. For example, two molecules of the sodium acetate reacts with the water to form electrolyzers. Ethane plus 2 molecules of sodium hydroxide plus hydrogen plus 2 molecules of CO2 is eliminated. So here 2 RCOO, 2 RCOO minus 2 electron means or plus 2 CO2. R plus 2 CO2 is, and then 2 Na plus will be there, 2 electron minus means 2 Na at cathode. So 2 electron minus 2 Na, and then this reaction is believed to occur in the following steps: 2 CH3 C double bond O Na plus means O minus 2 Na. That is 2 CH3 C double bond O minus plus 2 Na, and then 2 molecules of the water means ionization, 2 OH plus 2 H plus at anode. 2 CH3 C double bond O minus means 2 molecules of electron will be eliminated. So so we are putting it as a free radical. So 2 CH3 C double bond O free radical, and then this is the mechanism: 2 CH3 C double bond O free radical, 2 CH3 is eliminated, and C double bond O, and the double bond is shifted here, and then H3C CH3 alkane is formed since the discharge potential of the CH3CO is lower than that of the OH. Therefore, CH3CO is ions are preferably discharged at the anode. OH minus remain at the solution. So, since the discharge potential of the CH3CO minus is lower than that of the hydrogen, therefore CH3CO minus is preferably discharged at the anode. OH minus remains at the solution. At cathode, 2H plus 2E minus is a hydrogen. And since the discharge potential of the hydrogen is lower than that of the sodium ion, hydrogen ion is preferably discharged at the anode. OH minus ions in the solution. So this is the mechanism. Since the discharge potential of the hydrogen ion is lower than that of the sodium ion, therefore hydrogen ions is preferably discharged at the anode. OH minus ions remains in the solution. OH minus ions remains in the solution. And so since the discharge potential of the CH3CO minus is lower than that of the OH, therefore CH3CO minus is preferably discharged anode. OH minus remains at the cathode. So 2 hydrogen plus 2 electron, it gives hydrogen. Since the discharge potential of the hydrogen ion is lower than that of the sodium ion, therefore hydrogen ions is preferably discharged at the anode. OH minus ions remains in the same solution. So this alkane is completed.